Hi, I'm Dr. Andrew Bernard from Michigan Tech University, and I'm here today at PCB Piezotronics to demonstrate the concept of decibel addition from two sources. Today we'll be using a laptop computer, compact DAC system with an 9234 card, a two-channel loudspeaker, and a PCB Piezotronics model 378 BO2 half-inch condenser microphone. So let's take a look at the theory. The equation for converting a sound pressure to a sound pressure level is shown here. We take 10 times the base 10 logarithm of the total pressure squared divided by the reference pressure squared. And what we're interested here is this total pressure squared term. When we're adding two sources together, so P1 and P2, the pressure squared is the square of the sum of those two sources. And what we're concerned about in this demonstration is this cross term, 2P1, P2. Whether that cross term is present depends on the type of sources that we're adding together. Now, most commonly, probably over 90% of the time, we'll use incoherent source addition. That means that the sources have no consistent phase relationship with each other. So in this example, we've got sound from an automobile and sound from a chainsaw. The expected value of that cross term is going to be 0 because there's no relationship between those two sources. So the total pressure squared is just P1 squared plus P2 squared. And if we have two sources of the same level, say 60 dB plus 60 dB, the result will be 63 dB. So we get a 3 dB doubling per doubling of sources. In the rare case when you have a coherent system, now we have two sources that do have a consistent phase relationship. So in this case, we have two pumps that are synchronized or timed together. Here we'll have the cross term will not equal 0. And what will happen when we add two levels together, say 60 dB and 60 dB, we'll get a 6 dB increase per doubling of source. And that's because the cross term is now present. We'll start with driving a single speaker with white noise, and then we'll add the second speaker with incoherent white noise, meaning the same RMS value, but a totally different signal. Then we'll run the same signal to both speakers, and that will be coherent noise sources. You'll notice for this demonstration, we have the microphone sitting on the table and now off the stand. So we'll start the white noise and take a baseline level with a single speaker. Our baseline level is 75.7 dB. Now we'll turn on the second one with incoherent noise, and you'll see on the screen that the two signals are different. And as expected, we see that 3 dB increase for doubling of incoherent sources. Now we'll make the signal between the two speakers coherent. And you can see that it's exactly the same signal, and we get a 6 dB increase per doubling of coherent sources, as the theory would predict. Next, we'll look at what happens when we add two sources together with different RMS values. Here you see a simple method for adding decibel levels. First, you choose whether your sources are coherent or incoherent, and then select the corresponding curve on the graph on the left. Select the decibel difference between the two sound pressure levels that you're adding and locate that point on the horizontal axis. Then move up to the curve you've chosen and left to find the decibel level to add to the higher sound pressure level to get the total sound pressure level when the sources are added together. An example of this pairwise addition is shown over here on the right-hand side. So we'll go through the first addition process to give you an example. Here we're adding 60 decibels and 57 decibels. So the difference is 3 dB. So we go down to our graph and we'll add these incoherently because that's what we almost always use. Up to the incoherent curve and then over to the left, and we find over here a value of roughly 1.7 dB. So that's what we add to the higher level, which would be 60 dB in this case. So the result of adding 60 and 57 is 61.7. If we do that for all 4 of these levels and do a pairwise addition, we end up with a total sound pressure level of 62.4 dB. And if we were to run the exact equation to add sound pressure levels, which you see on the bottom here, we'd get a level of 62.5 dB. So we get a very good estimate using our approximation curves and this pairwise addition process. Note that for incoherent sources, we typically ignore any sound pressure level difference greater than 10 dB, since 2 sources more than 10 dB apart do not significantly add level to the higher SPL. This becomes an important point when discussing background noise in our measurements, which we'll discuss in a different demonstration. So to demonstrate the points from the last slide, we will drive both of these speakers with incoherent noise, and then using the vertical slider bar you see on the screen, we'll decrease the relative level of the second speaker to the first speaker, and you'll watch the SPL difference decrease from the 3 dB we'd expect when they're the same level down to 0. So we have our two speakers running. You can see our 3 dB increase. And now we'll slowly decrease the level of one speaker with respect to the other. Now we're at a 10 dB difference, and as I continue to go down, make that difference bigger between the 2 speakers, you'll notice there's no change in the overall level. So the takeaways from this video are threefold. First, when adding sound pressure levels, it's important to understand if your sources are incoherent or coherent. Secondly, incoherent addition is by far the most common in acoustics. It results in a 3 dB increase for doubling of sound pressure level. And lastly, for incoherent sources, a 10 dB difference in levels between 2 sources results in no appreciable addition to the higher level. Thanks for watching. I hope this video was informative, and we'll see you next time.
For more information, visit PCB.com or give us a call at 1-800-828-8840.